Let us try to solve a problem based upon the surface integral. Now, in this problem, we need to find the total flux of this vector through the surface, which is given by z is equal to 4 minus x square minus y square, and only above the xy plane. Okay. So, in order to solve this question, first step should be to draw the surface. Okay. So let's try to draw this surface. So this is our x, this is our y, and this is our z. If you will try to draw this surface, let's first put the x is equal to 0, then you will be left with z is equal to 4 minus y square. Okay, and this is the equation in the yz plane, and this is the equation for the parabolic equation. Okay, so this is boundary in the yz plane. If you will put the y is equal to 0, then again equation in the xz plane would be z is equal to 4 minus x square. Okay, so it would be again parabolic equation. Okay, and if you will put the z is equal to 0, so the boundary of this surface in the xy plane would be, if you will put the z is equal to 0, it would be 4 minus x square minus y square, and it is simply x square plus y square is equal to 4. Okay, and this is the equation for our circle with radius 2. Okay, so the surface boundary in the xy plane is simply the surface, circle. Okay, so this is kind of surface we would get. Now the boundary, now this is the step 1. Okay, and this region is our circle with x square plus y square is equal to 4. Okay, now okay, we have drawn the surface. Now I gave you the expression for the surface integral in the last lecture. This it is given by f dot n cap multiplied with ds and integral over the surface s. And I told you that if you are given a surface in the form of z is equal to f of x by, then you can convert this surface integral into the double integral by putting n cap ds as minus del f by del x minus del f by del y 1 times dA. Okay, so now whenever you are putting the n cap ds in the form of dA, then you are converting the simply surface integral into the double integral. Now in order to double integrate, you need to find the surface in the 2D. What I mean, what is actually this dA is? So dA is the smaller region in the surface which you will get after taking the projection of this 3D surface into the xy plane. So if you will take the projection of this surface, you will get this circular region. Okay, in the xy plane. Okay, so this dA would be the smaller region in this circular region. Okay. Now, okay, that is fine. So we have taken the projection, and the projected region R is simply x square plus y square is equal to 4. Okay, it is given by the circle. Okay, that is fine. Now this would be kind of second step. Now what would be the third step? So let's just try to put the n cap ds, or let's first calculate the n cap ds. So our f of x by z is equal to f of x by is given by 4 minus x square minus y square. Yes, it is given in the problem. Now if you will find minus del f by del x, you will simply get 2x minus del f by del y, you will get 2y. Okay, so just put the expression into the surface integral. We'll get f vector is given as x, y and z dot product with this n cap ds, and n cap ds we have found as 2x, 2y and z component is 1 and multiplied with t. Okay, this is the surface integral expression. Okay, now let's try to solve this further. So after solving this dot product, you will be getting 2x square plus 2y square plus z, yes, multiplied with dA. So now it is kind of double integral. And what is the region? Okay, I have to write this r because now you have converted this surface integral into the double integral, because now you have converted this ds in the form of this dA. Okay, and dA is the region in the xy plane. So what is this region in the xy plane? If this is x, this is y, this is our circle with radius 2, yes, and this is x square plus y square is equal to 4. Now you have to calculate this double integral over this surface, okay. So now you can use the polar coordinate in order to solve this double integrate. So let's first put the value of z to further simplifying this. So 2x square plus 2y square, and z in this region is given by 4 minus x square minus y square, yes, and this is simply dA, and if you will solve this, it would be simply x square plus y square plus 4 multiplied with dA. Okay, now you can solve this double integration by the polar coordinate. Okay, this double integration you can solve by polar coordinate. So let's put x is equal to r cos theta, y is equal to r sin theta, and dA in this polar coordinate over the circular region is given by r dr d theta. Okay, so the region in the circular region, limit of the theta would be 0 to 2 pi, and the limit of r would be 0 to 2, yes, and x square plus y square would be simply r square, yes, plus 4 multiplied by dA. dA is r dr d theta. Okay, now if you will further solve, you can write it r cube dr d theta plus 4r dr d theta, yes, 0 to 2 pi, 0 to 2, 0 to 2, 0 to 2 pi. Okay, now I think you can solve this. It would be simply r4 by 4, 0 to 2, yes, and d theta plus 4 multiplied by r square by 2 with respect to r, yes, and it would be limit would be 0 to 2, and you will be remaining with this d theta part. Okay, now if you will solve this, it would be 16 divided by 4 multiplied by 2 pi, plus it would be simply 2 multiplied by 4, 8 into 2 pi. Okay, so it would be 8 pi plus 16 pi, which is 24 pi. Okay, so this would be our final answer for this question. Okay, so the trick is you convert the surface integral into the double integral by converting this ds into the term of dA by using this expression. Okay, and this expression is valid only if you are given the surface into the form of z is equal to f of xy. Okay, now if you do not have the surface into the form of z is equal to f of xy, I gave you a general expression. You need to parameterize the surface first, okay, into the u and b or maybe s or t or whatever two surface parameters. But once you have the surface into the parameterization form, then you can use the expression which I gave you. Okay, sure. Okay, thank you.